So far we have learned about what we can figure out from a function based on the first derivative and something called the first derivative test. So we always find where the first derivative is equal to 0. This gives us critical numbers. We put it into a chart. We see where things are increasing, where things are decreasing. Today we're going to talk about how the second derivative can give us information about a function and what that information is. So of course we've talked about second derivatives before, but the second derivative is the derivative of the first derivative. Okay, and what it tells us information about is not exactly the slope of the tangent, but it actually talks about how the slope of the tangent changes. So it tells us about the rate of the change of the slope of the tangent. So how is the slope of the tangent changing along particular intervals? Okay, so I'm going to give you guys a couple seconds here. I want you to fill out the first couple little things in this investigation. So I want you to find f prime at x, f prime prime at x, and see if you can figure out when f prime prime at x is equal to 0, and mark the points on the graph. And then you're going to just go through 2 to 4 here and kind of see if you can make some kind of conclusion for each of these. Okay, so I'll give you a few minutes to do that, work with a partner, and then we'll take it up. All right, so your first derivative here and your second derivative are posted. When we set the second derivative equal to 0, did you guys have a chemistry test today? Okay. You'll have some time after this, okay? Okay, when we set the second derivative equal to 0, we solve the same way as we would normally solve, so common factoring. We find that the second derivative is equal to 0 when x equals 0 and when x equals 1. So I've marked these points on the graph for you guys. So mark them off on your own graph as well. And then we're just going to go through a couple other little exercises here and then make some conclusions about what the second derivative can tell us. So use your pencil. And we're going to see if we can kind of use our pencil as a tangent line when x equals -1 and kind of approach 0. So the idea is that we'll start kind of like here, and then we'll move our pencil along. And once we get to 0, we should kind of see that the slope of the tangent is changing as we move along there. What did you guys notice about the slope of the tangent? What's going on there? So yes, it's negative. Tangent is negative, yes, and it's increasing. Okay, was it above or below the curve? It's below the curve. And what did you guys find as the value of f prime prime at -0.5? Anyone sub that in? What'd you get?
Same as the one next to it.
So did you sub in -0.5 in for the second derivative? You got 9? What did you get, Anita?
Oh, that's 9. Isn't it like 0.5? No, it's 9.
No, -0.5. I think it's 9. I think that's correct. Grayston? So we're just talking about from -1 to 0, this little section right here.
Oh, so it's negative and it's increasing.
Yep. Okay, so we'll unpack this a little bit more, what this can kind of help us with. But now I want to keep dragging our pencil to the right. We'll keep trying to keep it as a tangent line to the curve, going from 0 kind of toward the right now. So what happens as it's moving toward after 0? Let's do this in blue. So if we start at 0 and we kind of move forward from there. So it's negative and now decreasing. Well, when a curve is like, so the tangents are always kind of skimming the outside of the curve, right? So the red ones, notice that those ones are below the curve, and then as we transition to a curve that's like kind of facing down like that, now our tangents have to be above the curve to be tangent to the curve. So our tangent is negative and decreasing now, and we should notice that the tangent lines are above the curve. Essay? So it goes from 0, and then after that, it starts getting more and more negative. So, right, so we're kind of saying like as it moves through 0 and then afterward. So I'm taking a look at this little section right here, okay? From 0 to 1. Okay, and what is the value of f prime prime at 0.5, Anita? -3, perfect. Okay, and then what happens to the slope of the tangent as it moves through x equals 1 and forward from there? So I'll do this one in green. So here's x equals 1, we have a slope of our tangent, and then Grayson, what's happening here?
Positive tangent x.
So it's kind of like negative in this little section here, but it is increasing. So this section has both negative and positive tangents, but after 1, the tangents are increasing. They're starting negative, they go to 0, and then they start getting more and more positive. So we'll just say the tangent slopes are increasing. And we should notice as well that the tangents are now below the curve again. So why are the points where the second derivative equals 0 important? What do you guys notice about the change in the function? I'm just going to erase these tangent lines here, just so we can see the function a little better. What do you guys notice about the change in the function at these points? Anyone see anything, Anise? So we call this a point of inflection. What does that mean? So if we notice, this one's kind of like curving up, and then once we move to this section, it's kind of curving down, and then once we move to the other section, it's curving up again. So we call this concave up and concave down. These points, these red points that we marked off here, these points where the second derivative equals 0 is where we change from concave up to concave down or concave down to concave up. So there's a little summary here. Notice in this area right here, we are concave up. What did you notice about the second derivative in that area? Was it positive or negative? It was positive. So if the second derivative is positive, we are concave up, meaning like this. And if the second derivative is negative, what did you guys notice in this section right here? What was the second derivative? It was negative, right? And concave down. Yep. Shh, guys. Go ahead. So not x at 1, the second derivative at 1 is 0, but after that, so if we evaluated the second derivative at x equals 2, it would be positive as well because it's concave up in that area. Yep. Mm-hmm. So they won't be turning points. Turning points are where your first derivative equals 0. So the first derivative and second derivative, first derivative points are potential like local maxes, local mins. Second derivative, your zeros are potential points of inflection, so changes in concave, what we call concavity. Okay? Okay. So this should be our conclusion. When the second derivative is positive, so when we test it in that area and it's positive, that means that area is concave up. If we test it and it's negative, we think concave down. So think negative, sad face, positive, happy face, right?
So what has to be negative in slope?
Just when we plug in an x value into the second derivative, the value that we get out is negative or positive. Okay. So as Anise said, we call these changes, these areas where we switch from concave up to concave down or vice versa, points of inflection. Okay, so notice here we have this area that's concave down. There is some point that has to exist where we switch between the two, right? And that point is called a point of inflection. Now, these points can occur where the second derivative is equal to 0, or like we talked about yesterday with our first derivative and critical points. It could also happen, a possible point of inflection could happen when your second derivative is undefined. And what we would have to look at is whether the sign of the second derivative is changing on either side, just like we look at whether the sign of the first derivative is changing on either side to determine if we're changing from increasing to decreasing or decreasing to increasing. So same idea here. We want to see if there's a change in the sign of the second derivative or surrounding these areas where the second derivative equals 0 or is undefined. If your second derivative equals 0 and you find a value where your second derivative equals 0, it doesn't necessarily mean that it is immediately a point of inflection. It just means it's a possible point of inflection. We have to test on both sides to see if it actually changes from positive to negative or negative to positive. So we would consider, like when we found the x's of the second derivative up here, we would consider these to just potentially be possible points of inflection, and then we would have to see what's happening on both sides of those. Is there actually a change from concave up to down or down to up, right? And then if there is, then those can be confirmed points of inflection. Okay, so a good example of that is the function x to the exponent 4. The second derivative of this function is 12x squared, so it equals 0 when x equals 0. So at this point right here, that was just a possible point of inflection, but is there any change in concavity here? No. This is concave up everywhere, right? So there's actually no change in concavity, so this is not a point of inflection, okay? So we test, if we don't have a graph, obviously we test in the equation and we see whether it's changing or not. Okay, so I'll do some examples. You guys will kind of get the hang of it in a second. Okay, we can also use the second derivative to help identify local max and local min points. Okay, actually we call this like the second derivative test, so you can call it second derivative test. So we will check the critical points. So in other words, we'll check the areas where we found the first derivative was equal to 0 and see if we get positive or negative for the second derivative at those points. So what happens is if I sub in a potential, or not a potential, but a critical number, that's potentially a local max or local min. If my second derivative gives me out a positive value, okay, that's what we mean by greater than 0, that tells us the area is concave up. So what does that tell us about the potential critical number? Or not potential critical number, but the critical number and potential local max min. It's a local min, right? So if the area is concave up, we must have a local minimum at that point. And if the second derivative is less than 0 or negative, that tells us we're concave down. So our critical number must be a local maximum. Okay, so those are really quick ways that we can test critical numbers. However, sometimes this test does fail. If we happen to plug in a critical number into our second derivative and we get 0, that means the second derivative test has failed and we need to resort to using the table from the first derivative test. Okay, so there's a little note for that. Pardon? So if we plug in a critical number into the second derivative and it equals 0 rather than a positive or negative number, then the test fails from the first derivative. to the second derivative. Yep. Yep.
Can we do this? So it says, we use the first derivative test, so what would we put into the chart, like the critical numbers?
The critical, yeah, same as we did in our previous lessons. You just create the chart with the critical number and then test it in the first derivative to see whether it's changing from increasing to decreasing or not. Right. Okay, so you guys will kind of understand what we mean by all of this once we do some examples, I think. So let's scroll. There's a little summary on this page for you guys. It tells you basically all the information we can find from a function, so just a regular f at x function. It also tells you the information that we can find from the first derivative. And it also tells you the information that we can find from the second derivative. So that's kind of just like a summary of all the pieces of information you can gather from all three of those different things. Okay, and then there's just a summary of how you can test critical numbers. So hopefully that's helpful for you if you're looking back.
Is there anything you can find from the fourth derivative?
Or the third derivative?
Or yeah, the third derivative.
I think like most of this gives us like basically all the information that we need from the function. So yeah, the third derivative isn't like super helpful to us. Although we could keep finding derivatives if we want. Yep.
Why do you end up with 0? If you keep going.
Okay guys, there's lots of chatting happening. If someone else, especially your classmate, is speaking, you need to not talk, okay? Okay, Michael, sorry, go ahead.
Wait, so why is it you keep finding derivatives, you'll end up with 0? Like, why is that?
So eventually, when I keep taking a derivative, eventually, remember we talked about how the degree drops every single time?
Oh, but you get to degree 0, it's 0.
Right. Is that what you're asking? Or you were asking why are we finding where it's equal to 0?
No.
Oh, okay, yeah. So eventually the degree will drop so much that you're just left with a constant, and then, at least with polynomials, yeah. Yeah. Okay, so types of questions that you might see for the function f at x, find all points of inflection and the intervals of concavity. Okay, so we are going to, if you see points of inflection and concavity, you want to think second derivative. Okay, so we're going to find, of course, the first derivative before we find the second. And to find possible points of inflection, we set the second derivative equal to 0, okay, just like you guys did in your investigation. And we're going to solve. So difference of squares here. And when we find these x values, I'm just going to wait actually until everyone's ready here. Okay, when we find these x values, if we want points of inflection, we're thinking xy coordinates. So I'm just going to take these x values and plug them into f at x. We'll just calculate quickly here. So I think we get -10 for both of these. Okay, so -110 and 110 aren't necessarily points of inflection, they're possible points of inflection. And we have to do a little test with the second derivative to determine whether they actually are. So is there a change in concavity or not? Derek? Yes, thank you for both of those. Okay, so we're going to set up a chart similar to our first derivative chart that we've done the past few lessons. And I'm going to, again, order these lowest to highest. This time we're plugging into the second derivative. Okay, this is the second derivative test. And then it's going to give us information about f at x. So choose some test values here. And we're going to plug them into the second derivative. So either in its expanded form, or you can use the factored form if you want, whatever works. I think we will get positive, negative, and positive here. Okay, now we're testing in the second derivative. This doesn't tell us about increasing and decreasing. This tells us about concave up and concave down. So we said positive second derivatives cause concave up or concave down?
Concave up.
Up. So this section is concave up. Okay, same with the last section here. Okay, and then the negative section, this is going to be a concave down section.
This next switch to 0, it means it failed, right?
If the second derivative equals 0.
Oh, yeah, right.
But we can use a test value of 0 for sure.
Oh.
Okay, so are -1, -10, and 110 points of inflection? Yes, there is a change from concave up to concave down, and then down to up. So this must be a point of inflection in between here. Same thing here, point of inflection. So we could further say now, therefore, -1, -10, and 1, -10 are points of inflection. I'm just going to say POI, if that's okay with you guys.
What if it goes negative, negative, positive?
Yeah, so if it goes negative, negative, positive, the first one would not be a point of inflection. And then the one where it goes from negative to positive, that would be a point of inflection. Okay, so similar to how we do intervals of increase, decrease, this question's asking us about areas that are concave up and concave down. So we're just going to give the intervals over where these occur. So concave up areas happen from negative infinity to -1, and 1 to infinity. If you like inequality notation, where x is less than 1 and greater than 1. Either one of those I'm fine with. You choose what you feel most comfortable with. And then concave down is from -1 to +1. Or again, in the other notation, inequality notation, should look like that. Any questions on this one? It's pretty similar to like what we do with the first derivative, right? There's a lot of kind of repetitive analysis, but extra things that we can find here. Can I scroll from this? Are we all good? Okay. So the second part of what we were talking about on a couple pages ago is classifying critical points or critical numbers using the second derivative test. So how can I tell if a critical number is in fact a local min, local max, or neither point using the second derivative test? So the first thing that we need to find are the actual critical numbers and the critical points. So we're going to use the first derivative to find those. And I want to know where the first derivative equals 0 to find the critical number or numbers. So we're finding critical points, which comes from the first derivative. And then we're going to use the second derivative test to classify those points. Okay, quickly, because it asks for critical points, we're thinking xy coordinate. So I'm just going to plug g at 0 in and g at 2 in so we can get their y coordinates.
Just say that they're possible.
So these are critical numbers. They're possible local extreme values, right?
What does that just mean? Possible.
So these aren't, again, these aren't points of inflection. These are critical numbers.
Oh yeah, I'm thinking about.
Yeah. If we found where the second derivative equals 0, then we would say, okay, these are possible points of inflection. What do we get for this? 8 plus 2, so 10 minus 12, negative 2.
So if it says to find the points of inflection in concavity, we just go to the second one.
Yeah.
And then critical points, okay.
Yep. I did that right? It's negative 2?
Yeah.
Okay, so our critical points are 0, 2, and 2, negative 2. Okay, so we found the critical points. Now we're going to classify them using the second derivative test. Okay, so when we say classify, we mean like, are they local maxes? Are they local mins? Are they neither? So in order to use the second derivative test, we're going to find the second derivative. And the test is this. All we need to do is we need to plug in each of the x values from the critical points, or just these critical numbers from above, and see whether the second derivative gives us a positive, negative, or equal to 0. If it's equal to 0, the test fails, and we need to go back to the first derivative test. So I'm going to evaluate g prime prime at 0. I'm not so much interested in the number as I am interested like whether we get positive or negative. So here we get negative 6. Now when the second derivative is negative, what does this tell us about our function? It's concave down. So at 0, 2, what do we have? I thought I heard it back there. Anita, did you say it? Was it you, Alex? Local max. Okay, so this point is now classified as a local max. Of course, if it's concave down in that area, there can only be a local max there, right? Okay, and then we'll evaluate g at, or g prime prime at 2. We get 6. And when the second derivative is positive, this should tell us that this area is concave up. So therefore, we must have a local min there. Yeah. Okay, so that's how we can just use the second derivative rather than that first derivative table in order to classify some of our critical points. Any questions, essay?
Just classify just means there's no local max on
Local min, local max, or neither? Yeah. Okay. And now your favorite questions. We're going to sketch possible graphs. All right, so this time we're given information about a couple different things. We're given information about the second derivative, we're given information about the first derivative, and we're also given information about the regular function. So let's just start with the easy one. We can graph f at negative 3 equals 9, right? Just graph the point. Okay, we also have a little bit more information about the x value negative 3. What does it mean when the first derivative is equal to 0 at an x value?
Turning points.
If f prime at negative 3 equals 0, this must be a critical number. So So there's probably a turning point here, right, when the derivative is equal to 0. So we have a little bit more information that can help us classify that maybe a little bit further. It says f prime prime is negative for all x values. So if the second derivative is negative everywhere, what does that tell us about our entire graph? It must be concave down everywhere. So if it's concave down everywhere, I think we can confidently say that f at -3 must be a local max, right? Yes, essay?
Why is it?
Because it's concave down everywhere. So it equals -2, right? For all x, that's what it tells us. Okay, so that means that we must have just something like this, right? Oh, that was bad. With a local max at -3,9. Any questions on that one? No? Okay, let's try one more. Okay, this one's a little bit more, gives us a little bit more information. It's got a few more pieces here. So we know the second derivative is less than 0 or negative when x is less than -1. So I'm just going to put a little marker here at -1. So our graph is concave down from basically -infinity to -1, right? Less than -1. It's concave up, so this tells us the second derivative is positive when x is greater than 1. So it must be concave up after that point, so from -1 to infinity. Okay, we also have a couple other pieces of information. So we have two areas where the first derivative equals 0. That should tell us that those are potential local maxes, local mins, so they're critical numbers. Okay, so these are potential local maxes, local mins. I think because we know the areas that are concave up and concave down, we could further classify these. So -3, this occurs in this interval, in the concave down interval. So yeah, this one's a local max. And +1, that occurs in the concave up interval. So what does that tell us? Local min. Okay, so we don't know how high or how low these points go. We don't have any information about f at -3 and f at 1. So here's what you need to make sure. You need to make sure that this area is concave down, this one's concave up, and that your local min is along 1, and your local max is along -3. So choose a point. It doesn't really matter. You can put your local max there if you want, and you can put your local min there. And then there's going to be a point of inflection along right here, right? So along this line where x equals -1, it needs to change from concave down to concave up. So perhaps maybe we have something, that wasn't great. And then we change, right? So this right here is our point of inflection. Again, I don't know where this graph is shifted. I don't know if these local maxes and local mins are closer together or what, but as long as we have the correct information there that the question has given us, we're good. Any questions on that one?